Welcome. In this session, I will give an example of use of the summation formulas. Let me first list some of the summation formulas we might use in calculating Riemann sums. The first sum is quite simple. If you just add 1 from k equal 1 to n, you are just adding 1 to itself n times, that's n. Others are more interesting. The formulas for sums of natural numbers, the squares, the cubes, so on, turn out to be polynomials in n. So most often we will just sum them from 1 to n, and we get these formulas. The sum of natural numbers from 1 to n is n times n plus 1 over 2. The squares have sum n times n plus 1 times 2n plus 1 over 6, so on. There are other formulas, and then there's a formula for the so-called geometric series, which we won't really use. There is one more property of sums that's quite important. This is actually quite simple algebra. Basically, it combines two things. First is the generalized distributive law. If there is a factor common to all the terms in a sum, you can factor that out. And secondly, if you are adding numbers in a rectangular block, you can first add up all the rows and then add up the row totals, or you can add up each column, add up the column totals, and that's simply the grand total of all the numbers in that rectangular block. So if you have just two columns and each column has a common factor, then you can take the column sums, and in each column sum you can factor out the common factor, and that's what this says. Rather than to try to explain this, it will be easier to understand if I show you in a couple of examples how these are used. Let's find the sum from k equal 1 to 100 of 3k plus 5. So think of it as a rectangular block. First column consists of 3k, so 3 times 1, 3 times 2, all the way to 3 times 100. Second column consists of just 5. So I can split it up into column sums. In the first column, 3 is a common factor, so I can pull that out. Second column, 5 is a common factor, pull that out. Then the first column now is just 3 times the sum of natural numbers from 1 to 100. And if I use the formula from last time, remember this formula is just that says that this sum is n times n plus 1 over 2 if you sum natural numbers from 1 to n. So this will be 100 times 100 plus 1 over 2. And this is simply 100. 1 plus 1 plus 100 terms is 100. And then you calculate what that is. You can do this if you have appropriate summation formulas, no matter how many terms there are. Let's find the sum from 1 to 30 of k squared plus 2k plus 3. I'm going to do the same thing, split it up into 3, the sum of k squared, sum of 2k, and then sigma 3. In sigma 2k I can factor out the 2, and in sigma 3 I can pull out the 3. Then I use the formulas for sums of k squared, k, and 1. And these are the first 3 formulas in this list. So I'm just going to plug those things in with n equals 30, the upper limit for the sums. So for k squared from 1 to 30, I will get 30 times 30 plus 1 times the quantity twice 30 plus 1, the whole thing over 6. For the sum of natural numbers from 1 to 30, I get 30 times 30 plus 1 over 2. And the last one is just 3 times 30. And then you calculate this, and that gives you the sum. So hopefully this gives you enough of an idea of how to calculate sums of these types, which, as I said, we will make use of this in doing certain Riemann sums. I will stop here. Goodbye for now.